The bridge behind me is the Putrajaya monorail bridge. It was supposed to have a monorail going through it. The whole of Putrajaya was supposed to have a monorail actually, but in 2004 the project was shelved because of lack of funds. But the structure still stands as an iconic landmark in Putrajaya when you come.
The bridge is held up by large steel cables. These cables have been holding up the bridge since 2004. That's 20 years ago and without any maintenance. But since they aren't directly a threat to safety, they are just left there. Over the years, the steel rusts and weakens. They are under constant stress from holding up the bridge. Compared to 20 years ago, what is left of the bridge is sagging ever so slightly. A similar thing happens in prestressed concrete. The steel used for this bridge has the same high-strength steel used in prestressed concrete tensioning.
This massive anchor is holding down the entire bridge, one of 4. Imagine what would happen if this anchor would give way. Notice as well the tendons have this sort of white plastic around it. It's called sheathing. Keeps the steel from being exposed to rain, which prevents rust. So imagine what rust would do to steel cables like this. What would happen if those steel cables would break?
Understanding the limits and behavior of this steel is a key aspect of prestressed concrete. And when subjected to high stress, steel will elongate and weaken over time. This phenomenon, when it occurs in prestressed concrete, is called prestress losses.
Prestress losses are a very important concept in prestressed concrete design. In theory, we can design a prestressed concrete member which is applied with a predefined prestressing force, but in reality that prestressing force will never be transferred fully to the member. So prestress losses are a way for us to estimate how much reduction in the prestressing force that is applied to our member due to various factors, which we will see. This video will cover course outcome number 3, which is to analyze the influence of prestress losses and its effects on the design of prestressed members. As I've mentioned, the prestressing force, P0, or the jacking force, P-jack, will never be fully transferred to the prestressed concrete member. This is due to various factors which are grouped together and called prestress losses. There are 2 types of prestress losses in general. The first is immediate losses, also called short-term losses, while the other is called time-dependent losses, which you can guess is called long-term losses. Under immediate losses, we have elastic deformation, friction, and anchorage slip. Notice that elastic deformation only applies to pre-tension members, which we will see later why this is the case. Under time-dependent losses, we have creep, shrinkage, and steel relaxation. So this video will only cover the short-term losses. The first short-term losses, or the first category of short-term losses that we will cover, is called elastic deformation. So when we are applying some pre-stressing force to a pre-tensioned member, there is a phase where we transfer the pre-stressing force to the member itself. At this transfer phase, the reduction in pre-stress will occur because the concrete deforms slightly. Look at the diagram. Before concrete is casted or poured, the steel will be tensioned. This is why it's called pre-tensioning. Then the concrete will be casted onto the pre-stressing cables. After the concrete has reached its required minimum strength, then the cables are cut and the pre-stressing force is effectively transferred to the member. But the member will deform slightly. In the case of a concrete beam, it will deform ever so slightly due to its elasticity. And this deformation causes the reduction in pre-stress. So the remaining pre-stressing force after elastic deformation is P equals P naught minus delta P naught. P naught is our jacking force, while delta P naught is the change in our jacking force, or also known as our losses. So let's derive a formula so that we can estimate the amount of pre-stress losses due to elastic deformation. Consider a beam with a length of L. When it is applied to an initial pre-stress force of P naught, and when the cables are cut, it will deform ever so slightly, but I've exaggerated the diagram here, and the reduction in the length is delta L. So what is the strain in the concrete and steel? It's given by this equation. Strain is equal to, remember, the change in length divided by its original length. That's strain. So concrete and steel share the same value of strain because they deform together. Steel and concrete in a pre-stressed concrete member changes shape, changes length together. That's why the strain is the same. A strain decrease in steel will cause a strain increase in concrete. Now, why is that? Because as the steel relaxes or shortens a bit, because remember there's pre-stressing force applied to make it longer, the strain will increase. Then as that strain is relaxed, it actually causes the concrete itself to shrink. It causes a decrease in the strain, an increase in the strain of the concrete. So there is an inverse relationship occurring between the steel and the concrete. So we can represent this in the form of an equation. Negative epsilon s, or the strain in the steel, the decrease in the strain of the steel, is equal to the increase in the strain of the concrete, epsilon c. And since epsilon is equal to the stress divided by modulus of elasticity, because remember, modulus of elasticity is just F over epsilon. So you just switch the epsilon and the E, you'll get epsilon. You replace those values, you'll get this. The strain in the steel, the stress in the steel divided by the modulus of elasticity of steel is equal to the stress in the concrete divided by its modulus of elasticity. And we can rearrange it to get our stress in our steel on one side of the equation. And notice that a modulus of elasticity of steel divided by the modulus of elasticity of concrete, we can replace that with a simple ratio, which is alpha E, or the ratio of the moduli of elasticities. Then we have this negative Fs equals Fc multiplied by alpha E. So let's take this and convert stress into force. So what is stress? It's simply force divided by an area, P over A. So replace that in the equation, you get this. Remember, the force in the steel is the force in the pre-stressing tendon itself, the cable. So that's the change in the initial pre-stressing force, how much it's been reduced due to that strain action or the change in the length, that elasticity deformation there. So replace that. And you rearrange some of the factors to get delta P naught. and we label this as equation 1. So, to further elaborate, this change in the P naught is caused by the strain epsilon S, which in turn is caused by the stress F of S. So what is the stress in the concrete at the level of the tendon? Meaning, what is the stress at the concrete where the tendon is, basically, or where Y is equal to E, the eccentricity. So F of C, the stress in the concrete, remember your equations from the stress strain diagrams. It is negative P over A, the stress in the concrete due to the pre-stressing force, minus P EY over I, which is due to the eccentricity itself. And we can say that Y is equal to E here, remember? And EY becomes E squared. And we can rearrange, or we can take out the P over A to get our second equation. And you'll see why we do this, why we remove P over A. So substitute 2 into 1, you get this equation. Simplify it, and you get this, which is the change in the pre-stressing force is equal to that. So this is the losses due to elastic deformation, where alpha is actually the ratio between the modulus of elasticity of steel divided by the modulus of elasticity of concrete. So our very simple equation becomes a not so simple equation, but it allows us, when we rearrange it, to find the remaining pre-stressing force after elastic deformation losses. Don't confuse P and P naught. P is the pre-stressing force, whether it's the remaining one, the initial one, it's always the pre-stressing force, while delta P naught is always the change in that pre-stressing force or the losses itself. For post-tension beams, you don't have elastic deformation because when you apply pre-stressing force to a post-tension beam, the steel and the concrete will deform together. So as pre-stressing force is applied to the steel elongates and also causes, the pre-stressing force is applied to the concrete and the steel together. You apply the pre-stressing force to the steel transfers that force to the concrete as the force is applied, not in steps as we saw with the pre-tension members. There are no losses due to elastic deformation in post-tension beams, but there's a very special case or a certain scenario where you need to take into account, which is when you are post-tensioning a beam or member with more than one strand. If you apply stress one at a time to each of the strands, then you risk inducing elastic deformation losses. How? I just mentioned that there's no elastic deformation losses in post-tension beams, but now I mentioned there is. So which one is it? Let's see. If you have two cables in a beam, and for example, you apply stress to number 1 first, then no pre-stress losses occur. But once you finish applying the pre-stress to number 1 and you lock it off, then you apply pre-stress to number 2, then number 1 becomes slightly slacked. There's some release or relaxation in number 1 because you apply more stresses to number 2. So in this case, when you apply pre-stress to more than one cable at a time, when there are more than one cable or one strands, then there is a possibility for elastic deformation to occur. So how do you avoid this? You apply the pre-stress losses together, or you could either tighten or retighten all of the other strands. Maybe you could go back to number 1 and apply more stress to meet the same amount from number 1 to number 2. And this is something to take into account when you are doing design of prestressed concrete members and you have more than one strand. Okay, so the next type of short-term losses that we're going to be looking at is friction. So notice that these white colored pipes, they are ducts. Ducts for the strands to be placed inside once the concrete has been poured. So this is a concrete slab, a pre-stressed concrete slab, which has ducts for the strands to fit inside. And due to the nature of these ducts and due to the shape of them as they are laid out, notice they are laid out in a certain way for the moments to be occurring at the correct places, there will sometimes occur or there will occur friction. How does this happen? So when we have strands in ducts, they should have a smooth curvature like this. So we want the strand to be idealized as being perfectly in the middle of the duct, when in reality this doesn't happen. So in reality, they are not aligned and the strands will most often be touching the duct itself. It's very difficult to get a perfectly centered strand in a duct. So this misalignment actually causes some losses due to friction. There's some rubbing against the strand and the duct, which causes this friction. There are two types of friction as well. One is called curvature friction, while the other is called wobble friction. And even if the duct were smoothly curved, like you achieve perfect curvature, friction still occurs because the strand, sooner or later, at some point within the beam, the strand must touch the duct due to the nature of the geometry of the strand and the duct itself. You cannot have the strand curving without it actually touching the duct. It needs to touch the duct sooner or later. So basically, friction is caused by two things, curvature and wobble. In other words, whenever it touches the duct. So the one on the left is caused by curvature, while the one on the right is caused by wobble. And let's see some equations which we can use to actually predict these losses and calculate them. So friction losses depend on the change in the angle of the strand. Not all strands are perfectly shaped like that. Some strands might be having a very wide a wide array of shapes there. So there's many changes in angles. So let me just remove these pen markers. Okay. So if you take the force at section I, which is where we cut here, so that force Pi here is equal to P naught multiplied by E raised to the power of minus mu naught. What is mu? Mu is the friction coefficient and it depends on the surface roughness of the duct. This value is usually provided by the manufacturer of the duct itself. And theta is the aggregate change in slope, which is stated in units of radians, not degrees. So it is between the jack and the section I. Remember, it is the aggregate change, meaning the total change in slope. The curvature loss is P naught minus Pi, where Pi is taken from the top there, and we put it down there. So rearranging, we get P naught multiplied by this 1 minus E raised to the power of negative mu theta. If there is no data from manufacturers, you can just usually assume mu to be 0.19. And E, in this case, it's not the eccentricity, but it is E, the number, 2.718 dot dot dot. So that was for curvature. Now let's look at wobble. Wobble does not depend on angle, but it depends on the distance from the jack itself. So again, the force at section I here is P naught times E raised to the power of negative mu, but this time it's not theta, it's K multiplied by X. K is the wobble coefficient, depends on the workmanship, the quality of the installation of the ducts. It is the distance between the tendons, the degree of vibration using concrete, and the type of duct. It is a very abstract or very multivariable factor, but we can have some assumptions on it. X is just the distance of the section to the jack. So it's just basically that distance there. So the wobble losses are, after rearranging, P naught times 1 minus E raised to the power of negative mu Kx. And K can be in the range of 0.005 to 0.001 depending on the degree of workmanship. Better workmanship gives a higher number of K. So we can combine both of these equations. We can combine curvature loss and we can combine wobble loss. And once we combine them, we get a single equation. So the losses due to both curvature and wobble, which is categorized as friction, is P naught multiplied by 1 minus E raised to the power of negative mu multiplied by the quantity theta plus K times X. And remember, E is not eccentricity, it is the number E, the golden ratio 2.718 dot dot dot. It's kind of like pi, it's a constant value, it never changes. If you look on your calculator, you'll find the value of E there as well. Remember, mu can be taken as 0.19 if you don't have any data from manufacturers. That's kind of like the default value. And K is in the range 0.005 to 0.1. Now, the last type of short-term losses that we'll be going through is anchorage slip. So notice that this is a picture of a beam being subjected to post-tensioning. There's an anchor at one end here, and there's a jack at the other end. Now, one end is the live end, which is the jacking end. That's where the force is applied, while the other is what we call a dead end, which is just static, just resists the stresses applied to it. This is a typical picture of an anchorage, or where a cable would be anchored. This would be embedded into the member itself. So when we remove the jack, when the jack has reached the amount of prestressing force that we want it to apply, then we remove the jack. And when we remove the jack, there is some slight movement in the strands. They will slip slightly, sort of like something that is very slippery. It will move ever so slightly as they fit into the wedges. So at this part here, this is the wedge of an individual strand, which when we remove the jack, it will move ever so slightly into its socket. And this small movement, delta S, can be as much as 10 millimeters or 1 centimeter or even more, depending on how the anchorage is made. But this small movement of 1 centimeter or more causes some reduction in our pre-stress losses due to what? Due to the reduction in the strain of the steel. But unlike unlike other losses, anchorage slip, also called draw-in losses, they do not extend very far into the beam. Why? So let's consider this post-tension member and see. If there was no friction at all, maybe the duct was totally slippery or there was no friction, maybe the duct was lined with some grease, for example, then draw-in losses would be constant throughout the beam. From the end all across the beam, the losses would look something like this, the draw-in losses. But in reality, there is some friction, which we mentioned before, the frictional losses. These draw-in losses actually will stop at a certain point inside the beam due to friction. So as we get further away from the anchorage, the draw-in losses decrease. This part here is the draw-in losses, the part that I'm highlighting in yellow. And at a certain point here, it actually stops. And because of friction, the losses will get less as we go further into the beam. So think about why this happens. As we go further into the beam, the amount of surface contacting the ducts, between the ducts and the strands, it actually increases. There's more surface area, more length of cable, which actually touches the ducts, and there's more friction, which is achieved as a result. And this friction actually reduces the draw-in losses. It actually helps to hold the cable, the strand in place so that draw-in losses won't happen anymore. It just happens at the end of the jacking side. So you get this shape of curve. Now let me zoom in a bit more. You can see that the P jack will be the dotted line here. So if there were no friction between the duct and the steel strand, remember, the draw-in losses would start from here and it would just extend in a straight line. But since we have friction, this is what actually occurs. So this is the kind of shape that you would get. So friction helps to reduce slippage. So the shortening of the tendon due to this slip when we remove the jack is given by this equation. And the loss of force at the anchor, when we simplify, we get equation number 1, which is this. 2 multiplied by delta S, the shortening of the tendon, divided by the overall length, multiplied by modulus of elasticity of the steel and the area of the steel that we use. Remember that P and S are interchangeable. Some textbooks use P to refer to pre-stressing steel. Some of them just use S to refer to pre-stressing steel. The main reason why some textbooks use P is to differentiate the actual pre-stressing steel from the reinforcing steel, the steel which is not applied pre-stressing force to. So sometimes you would need to differentiate those two. And some just use PS, which further adds to the confusion. So the slope of this draw-in line can be estimated from simple trigonometry, shown by equation number 2 in the green box there. And when we let 1 equal to 2, remember what was 1? We'll go back a bit. 1 was the loss in the force, the delta P, the actual losses due to the shortening or this anchorage slip. And we can find a simple equation which shows us what is the distance at which these draw-in losses occur, which is from LD, which is the distance of LD, the actual draw-in losses. And this is LD here. So after this point, after LD, there are no more draw-in losses due to friction. LD is the extent of draw-in. And we can use this equation number 2 to find our draw-in losses, the actual value of the losses, or equation 1 as well, if you want. Both are fine, but that's how we get our anchorage slip. So to summarize, we have 3 different types of short-term losses. The first one is elastic deformation losses, and that's the equation there. Remember that alpha is actually the ratio of modulus of elasticity for steel divided by modulus of elasticity for concrete. Friction losses are given by this, where the P jacking force multiplied by 1 minus E raised to the power of negative mu times the quantity theta plus K times X. And E is 2.718, the constant or the golden ratio. And the last one is draw-in losses, which is estimated by this formula here, P jack minus PL divided by L times LD, and LD is the extent of the draw-in, or where the draw-in stops, because friction would actually hold the strand in place and prevent the draw-in losses from occurring further. So, in the next lecture, we'll be learning about the other one, time-dependent losses or long-term pre-stress losses. And we'll be doing some tutorials, exercises for short-term losses to see how we can calculate them and try to estimate them.